Good day, my viewers. You are welcome to Understanding Chemistry by Nkechi. Today's topic is looking at the concept of reaction quotient. So this Q is a symbol for what? Reaction quotient. Okay, so let's define reaction quotient. Reaction quotient is the ratio of the concentration of the products to that of the reactant under any experimental condition. Okay, let us consider this equation. Look at this equation. This equation. A reacting with B to give C and D. So I'm going to write, like I said, reaction quotient is a ratio of the concentration of the product to that of the reactant under any experimental condition. So reaction quotient. Let's write a law of mass action for this. So concentration of the product raised to the power of the stoichiometric coefficient times, so the one of D over that of A, that of B. So let us also write the one of K for equilibrium constant. Let me call this one equation 1 and call this one equation 2. If you look at these two equations, they look alike, they are similar. So they are similar. So what really happens is that the difference between reaction quotient and equilibrium constant is that the concentration of the species present, when I mean the concentration of the species, I mean the concentration of the reactant and product that is present may not be their equilibrium concentration. So let's look at the relationship between reaction quotient and equilibrium constant. So remember, reaction quotient can be calculated. If you know the concentration of this, and this, you get the value for that. If you also put this one, you get the value for this. So when Q is less than K, if the reaction quotient is less than K, so meaning that equilibrium constant is greater than what? K. So it means that the reaction proceeds from left to right. So it means that the reaction moves in the forward direction, favoring product formation. So what if Q is greater than K? So when Q is greater than K, so favoring the reactant towards formation. So what K? When Q is equals to K, so it means that the reaction is at what? Equilibrium. So at 350 degrees Celsius, the equilibrium constant Kc for the reaction. So this equation for the reaction is, so the equilibrium constant for this reaction is 50.5. Predict to which direction the reaction will reach equilibrium at 350 degrees Celsius. If we start with 2.0 times 10 to the power minus 2 mole of hydrogen iodide and 1.0 times 10 to the power minus 2 mole of hydrogen gas and 3.0 times 10 to the power minus 2 mole of iodine in a 2-liter container. So I want to solve this. So remember, the concentration, the unit of concentration is mole per dm cube. So I'm just giving only mole, number of moles have been given. So we're going to convert this mole to molar concentration. Alright. So let's look at the concentration of species present. So concentration, number of moles, divided by volume. Volume in liter or dm cube. So in this case, it's liter we are given. Alright, so I'm going to look at the molar concentration of hydrogen iodide. So the hydrogen iodide is 2.0 times 10 to the power minus 2 divided by the volume is 2 liter. So the answer is going to be hydrogen gas. So hydrogen gas, we have 1.0 times 10 to the power minus 2 divided by 2. This is mole. Divided by 2 liter. So the answer would be 5 times 10 raised to the power minus 2. Minus 2. Alright, so I'll begin the board so I have a space to solve this. iodine. Okay, so 3.0 times 10 raised to the power minus 2 divided by 2, so it should be 1.5 times 10 raised to the power minus 2 mole per liter. Alright, so having done this, we're going to put the formula for the reaction quotient. So concentration of the product raised to the power 2 to that of the reactant hydrogen raised to the power 1, concentration of iodine molecule raised to the power 1. So I'm going to substitute this value, this concentration into this. So the one for hydrogen iodide is 1.0 times 10 raised to the power minus 2. So that of hydrogen is 5 times 10 raised to the power minus 2 times the one of iodine is 1.5 times 10 raised to the power minus 2. So divide this value, Q is going to be 1.33. So this is the value for Q. Then we are given that Kc is 50.5. So for us to predict the direction of this reaction, so what it simply means that Q is less than K. So I said when Q is less than K, what simply means that the reaction moves from it moves from left to right. It moves from left to right, favoring what? Product formation. You write it. Okay. So I can also say the forward reaction is favored, or the reaction moves forward, favoring product formation. So you are saying correct. So let's look at another question. The decomposition reaction of ammonia was carried out in a 4.5 liter vessel at 490 degrees Celsius. The number of moles initially present was 2.49 moles. At equilibrium, the amount present was 0.35 mole. Use the data to calculate Kc and Kp. Okay, we're going to start. So if the initial amount that was present is 2.49, and at equilibrium you have 0.35. So we're going to find the amount that decomposed. So let's write the equation for the reaction. So let's look at the initial amount that's present. Initial amount. So amount is certain as what? Moles. The number of moles initially present was 2.4. Now that's with this reactant. So this is the amount of present initially is this. This one was not present and then we formed. So for here you have 0.00 mole, 0.00 mole. Okay. So let's look at change in concentration. Change in concentration. So if this 2.49 was present initially, and at equilibrium we are getting 0.35. So what's the change in equilibrium? Means the one that decomposed is what I'm looking at. So remember, we are going to use negative sign because the reactant is going to do what? Disappear. When product appears, we use plus. So how do you get the change in concentration? Simply do this minus this. 0.35 minus 2.49, which will give you minus 2.14. So change in concentration minus 2.14. So change in concentration here. Okay, look at this. I have 2 moles here. So the mole ratio for this is 2:1:3. So the change in concentration of this one is 2.14. So change in concentration, I'm going to find the number of moles. Change in concentration for this 1 mole of nitrogen gas. So what it means is that 2 moles of this produce 1 mole of this. Therefore, 2.14 mole of this will give you what? Dash. So it means that for 1 mole of this, When you divide this thing by 2, you get what? The one for what? For nitrogen gas. So which will be plus 1.07. So this one is 3 moles. How do I get for this? It's going to be say 2 moles of ammonia produce 3 moles of this. So therefore 2.14 will give you the one of hydrogen. Or simply do, since I know the value for 1 mole, if I type 3 times this value, will give you this one. Or if you do that sentence, you still get it. If you do 2.1 times 3 divided by 2, it will give you the same answer. So what I have here is 3.21 mole. Okay, we're going to look at equilibrium amount. Equilibrium amount. If this question, if I have, for example, if I'm not giving mole and you're giving concentration, I wouldn't have done equilibrium amount. What I've done, I would do straight is equilibrium concentration. So this minus this, equilibrium amount will have 0.35. Of course, that's one in the equation here. So 0.35. So if I add this in together, I'll be having 1.07 mole. This one is also mole. So if I add this in together, 3.21 mole. So this question is best done in a tabular form like this. So we're going to look at equilibrium concentration. Concentration in mole per liter. Okay, so look at this. Concentration in mole per liter. So this is mole, 0.35 mole. So the volume of the vessel is 4.5. So we divide it by 4.5 to get the molar concentration. So we have done the calculation of the concentration of the species as present. So applying the law of mass action, so Kc, so the reactant is N2, concentration of reactant times concentration of product. So raised to power 3. So that of ammonia raised to power 2. So I'm going to substitute this concentration value into this. So we're having 0.2238 times 0.713 raised to power 3 divided by 0.0778. So raised to power 8. Okay. So Kc is equals to 0.08627, so divided by 0.00605. So by the time we do that, the value of Kc is going to be 14.2. So value of Kc is 14.2. We have to calculate Kp. So Kp is equals to Kc times gas constant and temperature raised to the power change in a stoichiometric coefficient. All right, let's put our parameters together. Change in stoichiometric coefficient. You can see now. So on the product side, we have 1 mole of nitrogen and 3 moles of hydrogen. So 1 plus 3 minus. On the right hand side, you have just 2 moles of ammonia. So 4 minus 2 is equals to what? 2. What about temperature? Temperature must be in Kelvin. So we are given a temperature to be 490 degrees Celsius. So R plus 273 Kelvin. So the gas constant here, except they are given the pressure in Pascal or kilopascal. If you are not given the pressure to be in kilopascal or Pascal, always use 0.08206. Okay. So I'm going to put our values. So Kc is 14.2 times The gas constant will have 0.08206 times temperature is 763 raised to power of 2. So Kp is 14.2. So apply this together, it's going to give you 3920.23. So what's the value for Kp? Okay, so this is the value for Kp. Right. So let's look at another question. 1 mole of hydrogen gas and 1 mole of iodine were heated in 1 liter sealed container at 500 degrees Celsius until equilibrium was reached. So assuming the equilibrium constant is 56.6, find the concentration of each species present. We have to find the concentration of hydrogen, concentration of iodine, and concentration of what? Hydrogen iodide. So we're going to write the equation for the reaction. It's not every time the equation for the reaction will be given, so know how to write the equation for the reaction. So 1.0 hydrogen gas and this were heated. So this is the reactant, hydrogen gas. So equilibrium sign. Right. So the equilibrium constant for this reaction is what? 56. Alright, so this is reaction. So like I said earlier, we already know the amount of hydrogen and amount of iodine that's present initially at initial time, but we don't know the amount that is composed or that reacted at equilibrium. Alright, let's start. So look at the mole ratio. The mole ratio of this of hydrogen, mole ratio of this 1 is to 1 is to what? Is to 2. Okay, let's look at initial amount. Initial amount. So I have 1 for iodine, 1.0 mole. For this one, there was no amount present. For the product, no amount was present at initial time. So let's have a look at change in concentration. Change in concentration. So that change in concentration, we are talking about the amount that decompose. So since we don't know it yet, so usually it's supposed to be the amount at equilibrium minus this one as initial time. So let's call it X. So use minus because this reactant is going to disappear. Minus X mole. Minus S mole. So products we use plus because product is going to do what? Appear. So next thing I'm going to look at equilibrium concentration. So equilibrium amount. Equilibrium amount. So 1 minus X. Add them up. 1 minus X. And this one is what? Is X. So equilibrium concentration. Equilibrium concentration is same thing because in this is time we're going to divide the mole divided by volume. So the volume is 1 liter, you see the same thing. When you are giving the volume as 1 liter, it is the same thing as because mole divided by liter. So mole divided by 1, it is the same thing as that. So 1 minus X, 1 minus X, and X mole per dm³. So in mole per liter. In mole per liter. So 1 minus X mole per liter. We are actually going to find what's the value of X. So the question is find the concentration of each species present. So this we are giving equilibrium constant. So we're going to apply the law of mass action to this question. Substitute. What's the concentration of hydrogen iodide? Oh, so that's I made a mistake here. Okay, look at this. Okay, look at this. So change in this concentration is S. If it's X, so since this one is 2, the mole ratio of this one is 2. So it's going to be 2 times this. So here will be what? 2x. Please take note of it, very important. If you make a mistake in this area, it means your answer will be wrong. Can you just get mark a formula for a formula mark? Please, very important. Always when it comes to change in concentration, note the mole ratio. Note it, very important. Since I have this one is 1 mole, and I have x. This one is 2 moles, is going to be what? 2x. So here is going to be 2s. Here is going to be 2s mole. So I'm going to substitute this value. 2x squared. So I have 1 minus x. 1 minus s is equals to 56.6. So 2x squared is 4x squared. If you factorize this, you'll be having 1 minus 2x plus x squared is equals to 56. So when you cross multiply and collect like terms, you come up with this. 52.6x squared minus 113.2x plus 56.6 equals to 0. So we're going to use the quadratic equation to solve this. So x is equals to minus b plus or minus square root b squared minus 4ac divided by 2a. Value s is equals to, what's b? Minus 113.2 plus or minus square root b is, so minus 113.2 squared minus, so 4 times, what is a? A is 52.6 times, what is c? C is 56.6 divided by 2 times 52.6. So by the time you solve this, you have 2 values. You have a positive value. S is equals to 0.79 and S is also equals to 1.36. So which of these values should we use? Which of them should we use? So we're going to use the one that's the value we're going to use must be less than the concentration, initial concentration we are being given. It must be less than that. So since this one is higher, this is not the practical value. So the practical value I'm going to use is 0.79. So since S is 0.79, we are going to find the concentration of each of those species that's present. So look at this. Concentration of hydrogen gas. So have it to do 1 minus x. So since x is 0.79, so it will now be 1 minus 0.79, which is equals to 0.21 mole per liter. So when you come across this kind of question, this is how to do it. First of all, they consider at a change in concentration, you are sent a number, letter, maybe 1. You put minus for reactant and plus for product. And always check the number of moles, stoichiometric ratio, number of mole, stoichiometric coefficient, very important. So that if this one is 1 mole, the other one is 2, you times it by 2. All right.